Hello and welcome to World Interferometry Day. My name is Peter de Groot and my lecture today has the provocative title, Does Interferometry Work? Now, of course it does, but interferometry has some interesting challenges and some fundamental issues when it comes to measuring surface topography, and I'd like to share some of these, some of the ongoing research which is occurring right now in the field of interferometry for surface topography measurement. Let's begin with just an overview of the kinds of things that people are doing with interferometry. Interferometers have been around for a long time. You can see on the right-hand side here a light box and a couple of optical flats and some interference fringes, sometimes called light bands. Then there's this fellow on the left-hand side who's using an interferometer to check some parts from many, many decades ago. Interferometers attract a lot of attention. You see these in a variety of different scenarios, not only in laboratories and research environments, but also in production. Interferometers dominate optical testing, the testing of lenses and mirrors and other components that go into optical systems. It's very natural to use optics to test optics, and interferometers are particularly good at that. But they're not limited to optical components. Interferometers have been built into microscopes using a variety of techniques: phase shifting interferometry, coherent scanning interferometry, and these techniques allow us to measure surface characteristics that are important to a variety of production applications as well as to research and development. The range of applications for interferometers is constantly increasing. It's now common to measure these very complicated shapes that don't look at all like lenses and mirrors. These are automotive components, and this can be done with interference microscopy as well as laser interferometry and other techniques. They're exciting new applications. Mixed reality is a really cool one that I like to get involved with in trying to test these new digital immersive displays that are being created using a variety of very complex optical designs and materials. It's really cool stuff. Although there are all these great applications, there still are skeptics. The results don't always meet expectations. You can have a very nice picture of this topography by interferometry on the left-hand side, showing a wealth of surface detail, but the reality is that the instrument response is falling off with lateral spatial frequency, meaning that closer together that features are, the smaller their relative height appears to be. And that variation can sometimes be disturbing for someone who wants to have a traceable measurement and is not used to an optical instrument and this transfer function characteristic. It's also the case that unexpected things can happen with interferometry, which kind of erode a person's confidence in the accuracy of the measurement. Here, for example, are surface topography features, about 100 nanometers tall, two rectangular features, and if you measure these things with interferometry, there's a good chance you're going to end up with something like this, where you have, these are sometimes called bat wings, you have these overshoots on either side, and we understand why this happens, and you can make adjustments in the way the measurements are performed, so this is not so prevalent. But nonetheless, it's something which can cause someone to take pause. So let's take a closer look at how interferometry works when we're looking at a three-dimensional object and why sometimes it doesn't work. Interferometry in principle is fairly simple. There are a number of nice lectures on the World Interferometry Day website that teach the principles of constructive and destructive interference and how that works. You get a bright fringe every 2 pi of phase shift, which is equivalent to every half wavelength displacement of the object mirror in this Michelson interferometer geometry that I'm showing in the picture. Using this principle, you'd think we'd be able to measure surface topography, and in fact you can, and there's lots of evidence for that. If you have two optical components that are in close contact, and you look at the interference fringes, you can relate that to surface height variations. Every fringe is half a wavelength of surface height variation, and that can allow you to even visually get an impression of what the difference in surface form is between these two components. So let's consider this surface topography and this whole problem of measuring the topography using interferometry. Is it really as simple as I just described? Well, here's the topography. And we want to measure this thing by shining some light on it. And when we shine light on it, what we find is there's a lot of scattered light. There's light going everywhere, and you can see these different diffracted beams going off in different directions. So can we really do interferometry on this type of a scattered light pattern? Will it work? It's really not so obvious. Is that we need to think about surface measuring interferometers as 3D imaging systems. They're not really just Michelson interferometers. They're quite different in that you have to take into account the imaging properties. So let's take a look at an imaging instrument, a conventional imaging instrument, not a 3D topography instrument. You got some source light, it comes down to an object, the light is diffracted, it passes through the optical system, it goes to a detector, and you record all of that information and you provide an image, a nice digital image here. Now the light which is diffracted from this object, you can figure this out, and let's assume that the object has no topography, it only has a variation in intensity. Then you get for a sinusoidal reflectivity pattern, you only get 3 diffraction orders, the +1, the -1, and the 0th order, sometimes called the DC. So fairly simple. You're only going to get these 3 rays diffracting off of this type of an object. In an optical system, there are various apertures, and that results in transfer functions, optical filtering. And the optical filtering is caused by this aperture here that I've highlighted, and it's going to block some of the high frequencies. And in an ordinary interference microscope, which has an extended light source, you can do the calculation. You find out that the response will gradually decline. So this is the picture that I showed earlier on, where you have this decline in response of the instrument as a function of spatial frequency. This is fundamental to imaging systems, even when they're not measuring surface topography. Now, a topography instrument is a little bit more complicated, although it has a lot of the same features. You got a light source, and now you've got an interference objective, but the light is still passing through an aperture of an optical system, going to a detector, and now we're going to use phase shifting or some other type of technique, and we're going to transform that into a surface topography. So like an imaging instrument, we're going to capture this light field, and we're going to interpret that light field in order to get our surface topography. So since it's an imaging instrument, there's going to be some relationship between the behavior of a regular imaging geometry and the geometry we're using here for topography measurement. The big difference is that even if you have a simple sinusoidal height object, you've got all kinds of diffraction orders coming off of this surface, off of this object. That's really kind of the fundamental difference. You don't have just the plus and -1 diffraction order plus DC. You've got all these other diffraction orders. The light is being reflected, if you will, off all of the different slopes and facets of the surface, and that creates a lot of extra light scattered off in different directions at higher angles than you would in an ordinary imaging system. Here we see that the number of diffraction orders depends on the surface height variation, as well as the frequency of sinusoids. In this case, we're just looking at sinusoids. So on the left-hand side, you see the far field diffraction pattern of a 0.04 micron peak to valley sinusoid. Let's keep the period the same, but increase the size of that sinusoid, and you see a whole number of other diffraction orders. And again, in an ordinary imaging system where you're just looking at intensity, the contrast of that intensity pattern wouldn't do anything to the diffraction pattern in terms of the number of diffraction beams that you would see. You would always see plus, -1, and 0. But in topography, it's a much, well, I'll call it richer. It's a much richer experience in terms of the kinds of far field diffraction patterns you can generate even from a simple structure. Large surface variations have lots of diffraction orders. So here we have 1.6 micron peak to valley sinusoid, again, pure sinusoid, and you see all kinds of diffraction orders, obviously not just plus and -1. Now, in order to do topography measurement, the key idea here is that the faithful reproduction of the surface topography requires that we capture all of the significant diffraction orders. So if we plot on this graph here, the far field diffraction pattern, we've superimposed on it the effect of the limiting aperture, the frequency cutoffs of the limiting aperture, what we find is that we need to get all of those diffracted orders within that limiting aperture if we're going to get the kinds of results that we would like to have, which is a faithful reproduction of the original topography. If you don't, then there are some consequences, some of which are not too surprising and others that are more surprising. The first result is that you have a reduction in surface height measurement response when surface features come very close together. So that's kind of familiar in that you expect that as you approach the Rayleigh limit or the Sparrow limit of lateral resolution, that your instrument response will decline. And that behavior is similar in a surface topography measurement instrument as it is to a regular imaging device. However, what's not so much the same is you can also get measurement errors, and that has to do with the fact that there's so many more diffracted light orders in an imaging instrument with surface topography, three-dimensional surface topography, than there are in an instrument that is just measuring an intensity pattern. So if you attenuate just some of those higher orders, what happens is you cannot faithfully reproduce, well, you cannot produce with perfect fidelity, let's say, the topography of the original object. Some of the topography results will be lost. And so you end up with a measurement error. So here we have a 320 nanometer peak valley surface structure. It's a pure sinusoid, but after we try to measure it with monochromatic phase shifting interferometry, we end up with 18 nanometers peak valley of error. And this is caused by this phenomenon of optical filtering of the higher diffracted orders. So for the most accurate optical topography results, we can derive from these observations a couple of rules. So the first rule is that the apertures must be large enough to capture all of the diffracted beams. So what does that mean in practice? That really means that you'd have to have a large numerical aperture for your objective if it's a microscope. And that might mean that you need to move to a higher magnification to look at a surface structure because of the surface slopes that are present in that structure, not just the surface detail, but simply the fact that you have large surface slopes. You might generate a lot of these diffracted orders that need to be captured within the aperture limits of the instrument. So that's a kind of a rule. And that means that you have to pay attention to your numerical apertures on your optical instrument. If it's a microscope, again, you might move to a larger aperture microscope objective. If it's a laser Fizeau interferometer, you might want to adjust your magnification accordingly so that you can capture all of that image detail. Now, what if the surface is not continuous? What if there's a sharp edge like those rectangular features I showed earlier? Well, the rule there is that those sharp edges and square profiles, the surface height variations are limited to much less than 1/4 of a wavelength if you want to avoid these kinds of fidelity problems that are sometimes seen, the bat wings and so forth. And that follows from the fact that if you have a sharp edge, there just simply is no way to capture the higher diffracted orders. And so you need to keep those under control. And for very small surface height variations, those multiple diffracted orders are not present. So this is kind of a rule which says that if you're doing interferometry and you have sharp edges or square profiles, you can expect it to be more difficult to get good results if the surface height variations are beyond this 1/4 wavelength limit. The instrument might behave in a nonlinear way. You can still do measurements, and a lot of people do, and you can do a lot of useful work if you don't have either one of these rules faithfully obeyed. But if you want to have a nice linear response and you want to be able to interpret your results in an easy way, these are the rules that you have to follow. Now, fortunately, these rules of the road for a linear response correspond to the most familiar and traditional uses of interferometers. So we're not really demanding anything exceptional. It really is saying that, well, if you want to push the boundaries of application for interferometry, you have to keep these rules in mind. Ordinary lenses, mirrors, and so forth, it's not that big a deal. But if you want to measure an additively manufactured part, you're going to have to keep this in mind, that you might be straying away from these two rules, and that has to be understood. You might have to configure the instrument maybe together with a good applications engineer, to find the best way to measure your parts. Given the desire to expand the range of applications for interferometry and surface topography measurement, and some of the considerations that I just outlined about the limitations of interferometers, there's a lot of active research. It's very interesting research into exactly how interferometry works when you're measuring surface form and texture. The traditional approach to looking at imaging systems, including interferometers that use imaging optics, is Fourier optics. And you can use a lot of Fourier optics methods to understand the foundations of interferometry. Traditional Fourier optics models can be quite useful. There's some simulators that are available that you could even download from Zygo.com or from my page on researchgate.com that show you how these work. And you can get a better idea of under what conditions you might need to use different numerical apertures and so forth. So these things are quite useful. However, they're not really the whole story. Microscope imaging in particular is a 3D problem. So there's going to come some point where trying to model everything in terms of two-dimensional wavefronts is just not going to work very well. People realized this a long time ago in confocal imaging and microscopy, that you really need to look at not the two-dimensional optical transfer function, but the three-dimensional optical transfer function and the corresponding 3D point spread function. So these are right out of Wikipedia, some beautiful pictures that Tom Vettenberg made showing conventional microscopy versus confocal microscopy and what those three-dimensional transfer functions look like. So it's lots of fun trying to generate those in MATLAB code. You can also do 3D modeling for interferometry, and you can get something like this picture here, which shows the 3D transfer function for coherence scanning interferometry. I won't go into a lot of detail about what the meaning is of this transfer function. If you look at it, it may or may not make sense to you, but it is very nice to look at. It is actually a very powerful way of understanding the instrument and for characterizing aberrations and correcting aberrations. Why is that? Well, because it accurately represents the true geometry of the measurement and the true geometry of the surface structure. So it allows you to calculate from first principles the scattering from the surface all the way to the formation of the signal that you will get back at the camera and the data that you need to analyze in order to get a surface measurement. You can also define the three-dimensional impulse response for interferometry. And the logic kind of goes from left to right here, that there's the traditional airy spot that everyone is familiar with who has studied optics. This is a slice through the point spread function. You can look at the other dimension through focus, and you have this three-dimensional point spread function in the other direction, showing the longitudinal effect of defocus. Now, if you look at an interferometer, the interferometer has interference fringes. And you can represent that with a three-dimensional impulse response. You can also call it a point spread function, but it has this unusual structure that it has these interference fringes in it. But it works the same way. You take this 3D impulse response and you can convolve that with a representation of the surface. That representation could be a very thin layer on the very top of the surface, sometimes called a foil. And that will allow you to calculate the interference signal. And the interference signal might look something like this for a sinusoid. Here we have going across the sinusoid, that point spread function convolved with the surface and generating these interference fringes. So we're looking essentially at an image stack as you scan through the part. This is the kind of thing that you would see, the interference fringes that you would see. And with this accurate representation of the interference fringes, you can test different algorithms. You can find out under what conditions you'll get good results. You could estimate uncertainty and so forth. All very important things to do in interference microscopy and interferometry for surface topography generally. Other things that have been going on in terms of modeling interferometers has to do with complex surface structures. For example, model-based thin film solutions are now part of commercial software. In these methods, a variety of signals are simulated internal to the software for surface structures that might involve film thicknesses varying here on the right-hand side from 0 to 1,000 nanometers thick. And the interference signal that you get varies with those surface structures, and you can use those models that are in the library and find out, well, okay, if I get a certain type of signal structure, that must mean that I have a film of a certain thickness on my part. And that allows you to do simultaneously surface topography measurement, film thickness variation, overall film thickness, and the substrate thickness. You can do all of that kind of measurement now in an interference microscope using a model-based approach. Another good reason to investigate analytical models for interferometers. So what comes next? What's the next step in our adventure in interferometry? Well, there's a lot to think about. There are a lot of mathematical tools that are becoming available, a lot of models of interferometers that are being applied like never before. The computing power is increasing. And again, probably more importantly, the range of application and the expectations of interferometers for surface topography, this is constantly increasing. So this is a challenge which we welcome because we like to do research and development in this area. But what we can safely say in response to the title of this lecture is that, yes, interferometry does work. All of these instruments that are based on the fundamentals of interferometry for surface topography measurement do provide results that we can have confidence in, and our confidence increases every day when we establish better and more reliable and more accurate ways of characterizing their response. With that, I'd just like to say thank you on behalf of World Interferometry Day and all the folks here at Zygo and around the world who are working in interferometry and who love interference fringes. Cheers, see you later.